Welcome everybody to session number 22 of my lecture on statistical energy analysis and hybrid methods. Today is the day of truth. We will talk about coupling loss factors. Coupling loss factors, that's the very important, very complicated subject of dealing with statistical energy analysis, and it's often omitted because it's complicated. With the derivation of the hybrid coupling loss factors due to the hybrid theory and all the stepwise derivation of source impedances or impedances of forces on infinite structural systems, this should be an easy thing, and we go through this procedure step by step with many examples. So, in the setup process of creating an SEA model, when we have fixed all the subsystem properties, the next step is let's calculate the coupling loss factors. Why do we spend a full chapter on this here in this lecture and also in my book? It's clear it's a very complicated task. It has to be explained in detail. However, the hybrid coupling loss formula gives a very clear and straightforward rule for this coupling loss factors, but we need the radiation and the total stiffness matrices of our junction configuration. This can be very complex. It helps to understand the coupling phenomena, and this is automatically important for noise control. If the coupling is bad, the noise control of our junction or setup is quite good. And finally, when we know the coupling loss factor, we can check if the weak coupling assumption is fulfilled in SEA. So how is the structure of this session, and how is the structure of the coupling loss factor chapter in my book? It's based on this famous hybrid coupling loss factor. Why is that? Because we can easily calculate, or it's a straightforward formulation, as I said. Here in this formula is everything you need to derive the coupling loss factors. You need the radiation stiffness of the receiving system for a coupling loss factor from M to N, the radiation stiffness of the sending system, here using the diffuse field reciprocity, and the total stiffness, which is a combination of all those matrices, both radiation stiffness matrices and the matrix that describe the structural, or let's say the deterministic system in the middle, if there is one. Good. So what we need is, as given before, we need the radiation stiffness of connected system. We need the dynamics of the junction, if it is there. And from this, we calculate the total stiffness matrix of all those quantities given above. The tricky thing is we have to choose the appropriate coordinate system, because this could decide then if this is an easy thing or if it's not. So it could be discrete space coordinates, it could be modal coordinates, and it could also be wave number coordinates. And we will give several examples of details that I will use here. So, or other coordinates depending on the nature of the junction. Maybe there's another option to describe the junction better by using specific practical coordinates. Good. So for each dimension, we will derive now in the following several radiation stiffness expressions. So point radiation stiffnesses, line stiffnesses, and area stiffnesses. And we will calculate the coupling loss factor out of it, but also the transmission loss or the transmission coefficient, using the expression here above. Before we enter the coupling loss factor business, we should again say a few words regarding the relationship between the transmission coefficient and the coupling loss factor. This is very often mixed up. Classic SEA is often based on wave transmission formulas. There's a practical reason because there are a lot of them that can be used. We will also use them. But you should know what is the difference. I mean, the coupling loss factor, that's the relationship more or less between the transmitted power and the source system energy. So the quantities are the power as given here and the energy of the sending system. The transmission coefficient definition is slightly different. That is the ratio of the transmitted power to the irradiated power. So that's something different. And As you know, there was a large chapter dealing with all the different dimensions of the diffuse field, and from these different dimensions we could derive a clear relationship between tau and eta for each specific geometry. So you might have different kind of junction configuration. 0D would be the connection of at least one one-dimensional system. A line junction would be something plate-like, and an area junction would be something that connects at least one cavity or whatever, or plate. So, however, there is an advantage for the transmission coefficient, and the thing is that we don't need any knowledge of the transmitting system. So here we have to know the energy, and this is not required for the transmission. It could be completely decoupled from the sending subsystem itself. Good. Again, to create the link, we have to modify how the energy is given. And the tricky thing is that you always have the energy density, and the easiest version is that the relationship between volume and energy density. If it's an area-derived system, you have to combine area and thickness. Or if it's, let's say, a one-dimensional system, is the length and combined with the cross-section, here given by AC. The irradiating surface of a junction area is either given by the surface area, by the line multiplied with the thickness or height, or it is exactly the cross-section. The diffuse field energy determines the normal intensity on this junction area. And the irradiated power that follows from this energy in the junction area is given by all the different dimension factors. So that's the surface times the intensity. This is equal to a kind of constant, beta d, we call it beta d, by group velocity and energy density. And if we just combine this back into an energy formulation, we will end up with this. So that means, and if we provide that the transmitted power is just the transmission factor multiplied by the input power, then we can formulate this relationship. So the transmitted power is just given by the transmission coefficient, and those equation using energy, surface, volume of the subsystem, speed of sound, and this constant that depends on the dimension. So with the relationship that relates the coupling loss factor with the transmission coefficient, we will get this expression. So the shape of the formula is always the same, but there is a dimension-dependent property here. At the end, we end up with this. So all the values are given here. That means that the relationship between coupling loss factor and transmission coefficient is given by those different quantities for 0D, 1D, or 3D junctions, 2D junctions, and you see that this that beta D was 1/2, given here by 2, 1 divided by pi, or 1/4. So, and so the good thing is that with this energy intensity relationship that we have derived based on our diffuse field theory, it's a clear and straightforward dimension-dependent relationship between transmission coefficient and the coupling loss factor. And putting all together, these are the formulas in all the different directions. So if we have the coupling transmission coefficient, we would like to get the coupling loss factor, we can use this formula. Keep in mind that here now we have used a clear relationship between all the geometry dimension and have replaced this by the modal density. So you will not find any volume here. You will find a lot of the modal density is expressed to use the geometry parameter. So now we have all sets of options of converting coupling loss factor to transmission coefficient for all the different dimensionality of the junctions. Good. So far for the diffuse field theory. If you remember well, that was also this diffuse field intensity was derived by, let's say, by a specific averaging over room, or let's say area angles. And sometimes we have to do this also in one specific angle. So if we have a 2D system, we would have to average the coupling loss factor over the half circle that could be that uses all possible angles. And this has to be averaged over the total angle area, and then this is the relationship for the two. This is the averaging procedure that you have to use for the coupling loss factor if we know the coupling loss factor for one specific angle. For the transmission loss coefficient, this is slightly different because there we need the normal intensity. This is considered by this factor sine of phi that gives us the normal intensity here, especially if we have a specific angle of excitation or wave impingement. And then you see that you get this expression here, so you have the sine coefficient. It is similar but looks slightly different because now we have the sine expression, which is missing in the coupling loss factor formulation. For 3D situation, which means an area junction, it means we have a half volume angle. The situation is the same. We have to use the volume angle. Due to the balancing of the angle, that there's a sine function in the angle itself. It has nothing to do with the normal expression. The integral looks slightly different, and we have to do the averaging procedure for the coupling loss factor using this integral, covering the half room angle for angle averaging, and we have to use again a sine theta. This time is a cosine function because the angle is now defined as the angle between the normal axle, not in relationship to the plane. Then we get this expression here. So again, that looks slightly different, but just to keep in mind, that's very important for you. We have different expression for the averaging of the coupling loss factor and the transmission coefficient. Especially in plane wave theory, this is very often used. You should keep this in your baseline formulas. Okay, good. So just one simplification. If we say that this angle, the transmission coefficient, is not dependent on the rotational angle, it becomes obvious that this simplifies much further. But this is a completely common and most common expression. But in most cases, you can use this one. Okay, so now, as mentioned, we go through this procedure step by step. And we start with point junctions. And now we give you some examples for different radiation stiffnesses of point junctions that should be used in the coupling loss formulation. For instance, bars and tubes, as in the configuration here like this. It's an extra force excitation here, and the wave would propagate into the one-dimensional system. We would get this radiation stiffness, and it's a scalar, because that's just 1 degree of freedom. And these are the expressions, so it would be the impedance density times the speed of sound in this area, and this would be given by this expression for simple bars. For instance, if we would consider bending waves, it would be the bending equation for a semi-infinite or for a finite beam, and just exciting it here in the middle, and then we would get this expression for this end configuration, and we would get this expression if we would use the point impedance just exciting here. If we have a plate system, as given here, then we have this surprisingly simple expression for, let's say, point force excitation in an infinite plate, which is given by this radiation stiffness expression. And you can now use all these radiation stiffnesses to calculate the potential coupling loss factor. So, and we do so now for some simple example. Just we start with a general configuration. Just imagine that there's a one-dimensional system here. This would be system number 1. That would be system number 2, which is connected here at this node. And the radiation stiffness of both systems is described by 1 and 2, D1 and D2. And this is would be kind of representative of a kind of inner junction stiffness, deterministic stiffness, which is here just given by a spring. That means we have the matrices are now scalars, which will be D1 and D2. The system in the middle would be given by this simple spring stiffness. The total stiffness is just the sum of all of them. And the inverse is also quite easy because this is scalar. It's just the reciprocal of the total stiffness, scalar. This would give us the so-called 0D expression for let's say for a simple junction. This will be the expression for the coupling loss factor, and this would be the expression of the transmission coefficient using this conversion factor from eta to tau. Quite a simplified expression that we have seen a lot in some wave transmission theory, as I will show later for the area junction example. Okay, that was the first simple one-dimensional or 0D coupling example. Now we come to a much more, let's say, practical example. Just imagine that you have a spring connection between a system. We have just a single degree of freedom radiation stiffness into the coupling world. It could be a 1D system, but it could be also a 3D system. We are just using the point radiation stiffness if you would excite in whatever created system. It could be machinery, it could be a fundament, it could be whatever. And then we have to use matrices again, because now we have 2 degrees of freedom. We have 2 degrees of freedom here, 1 and 2. And the stiffness matrix of the upper area would look like this, and the block matrix configuration of the lower would look like this. And as you know, the stiffness definition of such a spring in finite element conversion would look like this. If we put all this together, we get the following total stiffness matrix. Hooray! And due to the fact that it's just a 2x2 matrix, we can even find the inverse by using a reasonable effort. It's not too complicated, at least. If we do so, we have now again everything on board to calculate the transmission coefficient and the coupling loss factor, which will be done by this famous total stiffness triple matrix multiplication, and we would finally end up with this slightly more complicated expression. And dealing with all the mass and saying that we can neglect some of the different, let's say, indices, we get this expression here. So we could get back to scalars because we're just solving it. And we see that that's, again, a noise control feature. Now we know what is the nature of a spring, how soft does it have to be to create a reasonable isolation. Now, I mean, here it's the coupling, but or the transmission factor, but the lower it is, the better is the isolation. So that means we have to use the low stiffness. The imaginary of this stiffness must be low. You know that this is something that is related to radiation. And the denominator has to be as large as possible. And here it's completely, no, I don't care if it's imaginary or real, just the value has to be high. This is the rule of let's say, of designing such isolation systems. So it means if to get a good isolation, you always have to find very stiff mounting points in your systems. And related to these mounting points, you have to create a specific softness of your spring, which should be possible. I mean, if the spring is so soft that everything is pressed together, it's useless. But however, you know now what is the maximum isolation that you can achieve in terms of coupling loss factor. I will give you a fun example. Just check that we come back to the 2 bars connected by a spring example, because we can quite easily calculate these 2 bars, and we just assume that we have a specific coupling area and the stiffness given by the Young modulus and the density of the bar. So those are the quantities. And we assume now that we have the same material in a kind of similar cross section, and then we get this transmission factor, which we could express in a coupling loss factor. In our example, we say that this is the same area, we say the same density and same Young modulus. And now we use different spring stiffnesses, which are defined in relationship to the Young modulus and the area. So it would look like let's say, the same material, the same setup, but much softer. And the softness factor is given by gamma. So gamma of 1 would mean that the stiffness of the block in the middle would have the same as the other block. So what would be the final outcome of this? You would see here that's the radiation stiffness of our, let's say, system. So these are all the stiffnesses that I'm collecting here. and all that's the radiation of both. They are supposed to be similar, and this is the stiffness of the spring over the frequency range. And if we just represent the coupling, the transmission coefficient as transmission loss, so the logarithmic value, you see that only that if you have the very stiff spring, you have no isolation at all. Transmission loss is 0 in most cases. And in the other cases, you need a specific frequency. So always you see that once the radiation stiffness is higher than our related spring stiffness. So for instance, if now let's have a look at the orange curve. When the stiffness of the connection is higher than the spring, which happens here, this is the moment when we start to create a reasonable isolation. Just to keep in mind, your spring or your soft mount or your rubber mount definitely needs a lower stiffness than your connected structure. Easy and simple rule of noise control. So, as mentioned, you get a significant decoupling when the stiffness, the connection stiffness, is much higher than the spring stiffness of your connecting spring. So stiff contact points has to be selected at the mounting, and these stiff contact points allow quite stiff bushings because it's always a ratio between the mounting point and the bushing. Okay, good. So far for simple example of one-dimensional junctions. Now we step to line junctions. Unfortunately, I will not give you any example about line junctions. Why is that? By the way, this line junction took me 1 year because it's a specific case of the diffuse field reciprocity. It's not totally correct. It has to be modified. And it took me a while to find this out. And this is one reason why I will not present it here. Another reason is that line junctions, especially if you're talking about plates, are super complicated. Why is that? You have an incoming wave, and this incoming wave is reflected into 3 waves. If it's, let's say, a bending wave, it could be reflected into a longitudinal, shear, and bending wave. And at the same time, it is also transmitted into a longitudinal, shear, and a bending wave in the other plate. So it means you have hundreds of different, let's say, transmission coefficient, even if you're just thinking about one connection, because you have so many wave modes of propagation. The classical, let's say, degree of freedom that you use are kind of complex. It's a complex wave number based wave functions here at the corner. But the defining wave number is the wave number along the line junctions. And with this one selected line junction, it really depends on the frequency, how many, let's say, waves occur. I mean, if it's quite small, you have all possible waves. If it's getting larger, there's only let's say the shear wave and the bending wave. And if it's getting even larger, then you only have pure bending waves. So this makes the total setup really, really, really complicated. And it's not worth to put this in a lecture. It's much better to do this in self-study, again, as described in my book. Good. As mentioned, there are 3 ways of bending. Each type forms their own diffuse sound field. And in most cases, only the bending wave is relevant. Why is that? Because they have a much shorter wavelength and the other are still deterministic. And again, as mentioned, the diffuse field reciprocity has to be corrected. And the reason is that now the anti-Hermitian has to be taken instead of the imaginary. So it means the famous corrected diffuse field reciprocity would look like this for the stiffness formulation and would look like this for the impedance formulation. And if you use this expression also in the hybrid coupling loss factor, then it is correct, but it has to be used in this context, making things completely complicated. Good. So far for line junctions. But we can do a lot with area junctions, and we will now go step by step to all the different radiation stiffness versions of the area junctions. And we start with the discrete version, so the mesh-like radiation stiffness. And a quite good start to do so is the Rayleigh integral, because that's an excellent way to calculate a pressure due to, let's say, one position here at R0 radiating with a specific velocity. And we assume a regular mesh, and we say that I is the 0 position and J is the other position, which is the receiver position. Then we can, let's say, change from the integral formulation to a sum, using this expression here on top, and just summing up things and using the let's say the specific surface, which is the surrounding surface in this regular grid. From this pressure, we can then calculate also the force, but that is something we possibly will do later. There's one thing that has to be dealt with in detail when we have a singularity, when the radiation, the vibration point and the receiver is the same, so Ri equals Rj, then we use the radiation impedance of a piston. You know, this was a formula of the radiator when we dealt with fluid waves and the sources, which is given by this expression. So finally, just multiplying the pressure again with the surface gives the force. So we have everything we need. We have the displacement expression, we have a force expression, and from this we can directly calculate the radiation stiffness of a regular mesh radiating into a semi-infinite fluid. And the radiation stiffness matrix would look like this. And this is the those are the coefficients given by the mesh densities, by density of air, and this exponential expression. Only if the index is exactly the same, we have to use this one. That's quite practical. There's one thing to note for in a numerical sense. If you're using a regular mesh, you have the distance between, let's say, this point and this point is like this, and you will find it in many, many locations. So you can use that to really, really simplify your calculation, because this is always the same and you don't have to calculate this so often. This is used in the library Python, and this makes it quite fast, even to calculate the radiation of huge surfaces with lots of nodes. However, at the end of the day, this is some kind of very simple boundary element formulation, which would use somehow the same algorithm. Okay, so this is the discrete radiation stiffness. Now let's see what would be the case if we would use wave number coordinates, not the discrete coordinates. That means we assume a plane wave, which is radiating here from the plate, from the vibration. And this means that the plane wave is defined by kx and ky, and also by the z angle. This goes into this direction. So, however, just imagine that we have this surface velocity given by kx and ky, here expressing this, and from this and the physics of the fluid wave follows automatically the wave number in x, because it must all these wave number must be at the end of the day equal to the wave number of air. So we can calculate the z component by the wave number of air, and that's which comes from the frequency and the fluid properties. So when we say we use the pressure at z using this expression, we have the velocity, and from all this we can directly calculate the, let's say, the radiation impedance of the fluid half space for a given wave number pair, because that's the pressure divided by the velocity, and using all the above equations we will get this expression. The only drawback is that if the sum here of kx and ky equals ka, we have a singularity, especially for infinite planes. That will be dealt with later. Because this singularity is a very important thing, because this is something that's also very important to deal with if you do, let's say, if you have to design a radiating or have to prevent a radiating system. Just imagine that we take this radiation stiffness formulation, and for simplicity here, we just consider that ky is 0. And what happens if the acoustic wavelengths and the structural wavelength of the, let's say, the wavelength of the radiating surface is the same? and that's an infinite radiation stiffness. This would become 0, and that means that we say that the acoustic wave number coincides with the wave number of the radiating plate, and this is why we call this a coincidence situation. As given here, the air wave number and the structural or the radiating wave number is exactly the same. Another situation is that the Kx, the wave number, is smaller than the acoustic wave number. Then we will get an imaginary radiation efficiency, because this becomes here real, and that means that the radiation stiffness is pure imaginary, and this means that it is very efficient. In wavelength, it is a situation when the wavelength is longer than the acoustic wavelength. Because if the let's say the wave number is smaller, it means that the wavelength is larger. Good. So and the thing is, you will, depending on the angle, you will always find an angle where you can perfectly radiate into the free field, and where the, let's say, the projection of this wavelength to the structure would fit exactly to each other. Good. However, what would be the case when the Kx is much larger than the acoustic wavelength? This then gives a real radiation stiffness, and this is the so-called evanescent situation. Or again, arguing in the wave number field, you have a very tiny motion of your plate, and the air, which has much larger wavelength, cannot follow. So it means you just do some acoustic pumping. You are not radiating a wave. If you are sometimes at the concert or discotheque, you can feel the same effect in a bass loudspeaker. It's tremendous how much air is moved away at a bass speaker, but it's not radiating, because that's the same phenomenon. The speaker is quite small, the wavelength and the bass frequency is large. It could be meters, and then you have the same effect. Good. However, especially this coincidence here, let's say the infinite radiation stiffness, this is only valid, that comes from the infinite radiator situation. If it is a finite area, it's definitely not infinite, but however, it is high. So if you would like to avoid radiation, you should definitely avoid the coincidence situation. Good. Another option to describe the degree of freedom at an area is the so-called shape radiation stiffness. If we do shape radiation stiffness, it could be a mode shape. We do the same formulation again. We use the Rayleigh integral, but now we use a specific shape of the vibration given by this, for instance, function of W. And we can also do the same calculation. And then we take the radiated power just derived by this specific shape, and that means we have to integrate the velocity times the pressure, and the pressure follows from the above formula. You see that you have to integrate over the surface to derive the power, and we have again to calculate a second time over the surface to get the pressure. Means that we are ending up with a double integral, which means calculating the radiating power of specific shapes, making it quite complicated. However, we can use the discrete version that I have derived before. In this case, it would be the force that would come from the free field radiation stiffness using the discrete version of the area junction. And this double, however, but at the end of the day, this double integral is then converted into a triple matrix, let's say, at least a triple multiplication. So it's the shape multiplied by the radiation stiffness, and then again multiplied by the complex radiation stiffness, giving you the radiated power of a specific shape. Good. So, but what are we using this for? I mean, this can be used for, this is exactly the same situation like the so-called radiation stiffness in modal coordinates. If you remember, if I have one, let's say, real space matrix formulation, and I would like to shift it into modal coordinates, denoted by this prime, just to have to use this matrix conversion. The transformation matrix is the set of column vectors of the modes. If we go through the diagonal, it would be exactly this expression that I've shown you before. That means radiation stiffness matrices and left and right multiplied for specific modes. And if it is off diagonal, it would be a different mode shape multiplication. So again, this the diagonal is equal to the radiation stiffness, shape stiffness equation as described before. And also very important, just remember we had this funny formulation of the so-called radiation stiffness, which relates a radiated power of a vibrating structure to the similar radiated power of a plane wave of same velocity or displacement. And then we would get this expression here. So that means this is given by a clear formula. And this is just the surface average because the radiation efficiency is using an average velocity over a plate. And this gives us, let's say, another, let's say, approximated impression for the radiation efficiency. So it's the modal stiffness, radiation stiffness, divided by several quantities that describe the fluid and the shape, or let's say the statistics of your mode. Good. So, and however, the modal stiffness determines the radiation efficiency of modes. Why do we need this for? I mean, the good thing is if you inspect that, you see which form of your vibration is a radiator. And if it's a very specific mode that gets you into trouble, you can try to shape or to modify the mode shape to change the situation. Good. So, as mentioned, this radiation efficiency could help a lot to describe the area junction. And this is also the case for analytical formulations. So there is a theory in Leppington. So, I mean, the typical shape of our rectangular plate would be, we would have this solution. It's just a combination of sine numbers, which with these wave numbers in the plate area. And the funny thing is, even with this simple, this sine shape function, you cannot solve analytically the radiated power and to calculate the radiation stiffness out of this. I mean, I'm talking about the quantity here, which gives you the radiation stiffness. And here, this is what you have to solve in this analytical approximation. However, Leppington has introduced an approximation for this, and he did some, let's say, conversion. So the wave number is converted based on the acoustic wave number. It's normalized by it and be using R and alpha and beta, which are described in this axis. And mu is the, let's say, the length of any position here in this square. And then he goes through all the different steps of the coincidence area. I mean, this is the area where you have that means that we have equal wavelength of the structure and your fluid. This is the coincidence area. This is the area where you can radiate quite well. This is for if mu is smaller 1, and this is the more complicated area. So you don't have very good radiation, but at least you have some radiation. I will not go to all the details. Again, you will find the details in the original paper or in my book, but there's this approximation. I mean, for mu smaller 1, you can use this approximation, and for the mu higher, you can use this approximation. Then there is an even more complicated approximation for exactly the coincidence area, which is given by this quite lengthy formula. I will not derive it. It's just for mentioning it, and you have some different cases that has to be considered, and so on and so on. However, we have Python or numerics to implement this. So for exactly one, that's an analytical equation, and then it's represented by this. So however, if this is implemented and everything and so on, we can calculate using all these above formulas that we can calculate the radiation efficiency for a specific mode shape of a plate, applying the famous Leppington thing. And to give you a rough idea of that, there's an example. I just took a plate of this shape, 0.8 and a half meter, and I just used different modes of the plate and checked over the frequency range how well they could radiate. And the solid lines, they are representing the Leppington approximation, and the dotted and the small lines, they are using the shape function, but used in a discrete version using the discrete radiation stiffness. And what you see is that the analytical expression is very well fitting to the numerical expression in the area where the radiation is at least quite good. If it's a quite irregular plate, so you see that fits really well here in this area, but only if it's, let's say, in the lower mode shapes, things gets complicated and the approximation is not that good. But that's not a big deal because you always got a bad approximation in the area when your plate cannot radiate well. Okay, so this was now a different way of area junctions in terms of radiation of the area into a fluid. Something similar could also be the case if you have a plate. So just imagine that you have a classical plate and we know that the pressure is exciting this, and then we get a kind of displacement response, which is all given by this wave number pair kx and ky. And we know that we can use our say bending wave equation, because when we have pressure acting on the plate, we can only excite bending waves. And this would give this equation in wave number space between displacement and pressure. So hooray, we have everything we need to calculate the radiation stiffness out of it, because it's just the ratio of the pressure divided by the displacement. You have this double prime here, denoting that this is a kind of force per area, which is a pressure. So this is a stiffness per area, more or less. And this gives you this expression here. And if we formulate everything and get rid of our bending term using the bending wave number again, we would get this excellent expression here. You might say, hooray, that's an easy one again. So saying that the area radiation stiffness of a plate can be very well represented in wave number, which is the case for infinite plates. However, there's a drawback. You see, if this equals the bending stiffness, it's again infinite. Or it's zero, which is quite useless. That means for bending wave equal to the acoustic wave, if there is one, we would have, or at least when the wave number factor equals exactly the bending wave, it is zero. If there is dissipation, and there usually is always dissipation, you will get an extra. We have to express the bending wave number using our complex formula of it. And in that case, we would get this expression here for the plate with damping. But again, it would also only for a damped plate you would get a reasonable imaginary of your radiation stiffness. So again, you have to note, for practical thing, this is not usable. It looks nice, but we cannot use it for area junction calculation. Good. So far for the wave number representation. Now let's go to discrete version again. And here we are in a quite good situation, because we had this point excitation force and circular wave formulation, and the solution was given by this combination of Hankel functions. 2, 1 force in the middle. And here again, that's an easy thing. If we would like to formulate a discrete version of a regular mesh here, hooray, it's super easy. We just have to use this formula. So that means we have the forces here given. We have a specific distance that we know for the next point, if the point is located at I. And then we can calculate the matrix coefficient by just using the above formula. And even there is not even a singularity, if it's the same constant, we can use this expression if this is the I equal J. Good. However, we have to keep in mind this is not a stiffness matrix, this is a reciprocal of the stiffness matrix, so we have to invert it, and then we have the discrete stiffness of radiation stiffness of a plate. Good. So, so far for several radiation stiffnesses of cavities, semi-infinite cavities or plates, and now we use it in a coupling loss factor calculation. And we start with a very simple thing. We take the classical fluid-fluid coupling loss factor, because this is something that we know. So no plate in between. There's just, let's say, water and air, which is a typical combination of fluids. What would be the coupling loss factor between water and air? And you know that the stiffness wave in wave number domain was given by this, just considering that ky is 0 for non-specific reasons. And we can use the, and the wave number formulation has to be considered as a zero-dimensional coupling loss factor, because we just have for this wave number space, it's just one degree of freedom. And we can use the formulas that we have derived in the 0D junctions, and that's the transmission factor of the coupling of fluids, and this would be the coupling loss factor of this. And if you just keep in mind, in the fluid session we have derived this transmission of waves on two connecting fluids. So if you keep this figure here in mind, this is where we have derived that, and we have to reformulate it a little bit. So if we express our radiation stiffness as by the characteristic impedance, and using this angular forms of the incident angle and the transmitted angle, we would get this transmission coefficient formula. And this is exactly the same solution that we have derived when we have derived it by wave theory several sessions before. I think it was session number 4 or 5 or something like that. Good. What have we proven? We have shown that our coupling loss factor fits to the usual physics, which should be the case. Otherwise, we would be in problem. Okay, now we consider another kind of junction, but a very important junction. We just take an area junction. Now we have a plate coupled to a fluid. Yeah? So I mentioned that the wave number formulation of the plate is not practical, because we might have a zero result, but however, we do it in any way just to show you something. And that would be this case. That's the radiation stiffness of the plate. So again, we mentioned that we are in trouble if this fits the bending wave number, and then we have to use this expression for the imaginary or for the plate. And in addition, that's the other story, when the acoustic wave number fits all to this wave number expression, we also have an infinite radiation stiffness in the air part. So adding all together, we have a zero situation in the plate, we have an infinite situation in our fluid domain. So again, it's a pity we cannot use this formulation for the plate fluid coupling loss factor. But again, it is very important, because we can reformulate the coincidence situation a little bit. So when the acoustic wave number fits to the bending wave number, it's a very unpractical situation, because that's a situation when we have the so-called real coincidence. And this happens at a coincidence frequency given by this formula, or in angular normal frequency, it would happen by this. For a specific plate thickness and fluid properties, we can calculate the coincidence situation. And in technical systems, if you're using a single plate or whatever, you should definitely avoid coincidence. This is something why people don't like good technical acousticians, because to get a good coincidence, you need something soft. The bending stiffness has to be low to get a very high coincidence frequency. That means you have to take stiffness out of your plates. But unfortunately, all the other guys in technical systems, the engineers, need stiff plates, because this is where they are used for. So this is a typical target conflict. Good. However, so that means if we need to calculate the coupling loss factor of plates, we are lost, we can't use it, which is a pity. But there's a way out of this, because if you remember well, we can estimate the radiated power by the radiation stiffness. And this is the key feature. Yeah, we can use the Lappington formula for all these different wave modes of our plate. And when we are interested into the, let's say, the radiation stiffness of one specific frequency, you just have to integrate along the circle of all possible, let's say, directions of the wave number. And then we have to average about it. So how do we translate this, let's say, radiation stiffness into a coupling loss factor, a radiation efficiency into a coupling loss factor? So that's a formula for the definition of our coupling loss factor. And the energy is given by the area, the mass per area, and the velocity. So, and then we get for the coupling loss factor exactly this expression. And if we combine it with the upper expression here, we get a quite a practical and simple formula to get the coupling loss factor of a plate, just given by the radiation stiffness. So this is our way out of this wave number dilemma. So again, using approximative solutions for the radiation efficiency, we can then easily calculate the coupling loss factor. And again, as this let's say radiation efficiency is different for a specific let's say frequency, we have to integrate over the half angle and averaging over all the different versions and options of the radiation efficiency. So the radiation efficiency depends on the bending wave number and the angle phi of this, where we act at different, because from phi you get different wave number in x and y direction, and this is an averaging procedure that you have to create to estimate the radiation efficiency of a plate. This is also implemented in Piver, and this is also implemented in all classical, let's say, SCA packages. Good. So far for plate fluid connections. And again, this radiation efficiency is used by this Leppington approach as I have presented earlier. Okay, good. So I know you might find it boring, but I will again come back to the wave number domain. Because the situation is not that bad if you have a combination of fluid, plate, and fluid. So you still have the singularity issue, but the good thing is you get quite an interesting formula for the wave transmission of plate. So again, we use the transmission radiation stiffness in wave number domain now given by an angle, which looks like this. It could be two different fluids, but it doesn't necessarily have to be. We take the, and then we sum up all the stiffnesses using this stiffness and the stiffness of the plate, and we get this expressions here. So note that there's a 2 because we assume that we have the same fluid, and this is just the double version of this radiation stiffness. So this is our total radiation stiffness. And if we combine this then with the, let's say, the radiation stiffness into the connected other subsystem given by the above radiation stiffness of the two cavities, and going through the math, we can again use the zero-dimensional transmission coefficient, and we get this expression, and after some painful mathematics, we get this final expression for the transmission coefficient of a fluid plate fluid connection. Again, we have this full transparency issue when the wave number fits exactly to the bending wave number, but not the projected wave number, obviously. But and again, we can we have now different domains that are quite important. For instance, if the bending wavelength is much higher than the acoustical wavelength, we can neglect the bending term. And this is the case where we have forced motion of the plate. So that means the acoustic wavelength is very long, and it forces the plate to move with the acoustic wavelength because the structural wavelength would be much smaller. And this is the area we have which we call that's the mass law area, and we can neglect all the bending terms. And this gives us the classical mass law that you will also find in literature, depending on the angle. This is again another formula, which is the reason why people don't like us, because we have for a single plate which has no coincidence, the only way to increase the isolation is to increase the mass. To get 6 dB, you have to double the mass. And if you would further get 6 dB, you would even further double the mass. That would mean you would need 4 times the original mass. And this is, in many technical systems, not a good solution. But however, don't panic. For this, we have the double wall, which will be presented later. Okay. So, however, this is the upper limit of single plate transmission loss. This is the classical rule if we have perpendicular irradiation. And there are several approximations or corrections with experimental values for the mass law, but if it's just the typical angular mass law, you can use this one. Okay, good. So far for the wave number domain. Now we come back to the discrete space. Again, we had this funny formula which gives us, and we can use all the discrete versions that we have derived. If you remember, we had this regular mesh formula for the radiation stiffness into the fluid, and we had this regular mesh for the infinite plate. So for every force exciting a plate, we know the displacement. We have that. From this, we can derive everything we need. We have the radiation stiffness matrices, and we can calculate the total stiffness from equation 260 to 46. So this is the radiation stiffness for the fluid, and we use equation 259 for the infinite plate equation, but discrete version of the plate. So we have no longer any let's say mass formulation. But what we can also do is, that's a super simple thing. We just say, okay, I take a plate which has no stiffness at all. There's only mass. That means my stiffness is just given by a mass matrix. That means I just take the mass per area multiplied by the surface area of my element here. This gives us a very simple expression. This would be, let's say, the perfect expression of an infinite mass distribution. Good. So let's use those matrices in a numerical implementation. Anyhow, on top of that, to compare that, we can also calculate, let's say, the discrete mass law. That means we just have to average over all the possible angles, because the mass law formulation that we have was let's say, there was angular dependence on it, and this is done by this equation here. And however, there is a kind of maximum angle that is used by let's say, by Beranek, who said, I have the best agreement between my experiments and this famous formula when I use 78 degree. By the way, this is why you find as presetting in many commercial SEA packages this famous 78 degree. It comes from a paper from Beranek. Good. So, you see different versions. So here you see the blue line, which means full integration angle until 90, pi or 90 degree, integrating over the full half space. This is the orange line, is the famous curve of Beranek, and the green curve is the perpendicular waves acting on the surface. And the red line, that's the discrete version. So what is the discrete version? Just to keep in mind, give you back, that's just using this total stiffness formulation, using the discrete area radiation stiffness, and using the mass matrix formulation for the stiffness matrix. Then you get the red line. You see that Beranek was not totally wrong, but for, let's say, for the low frequency areas, the mass law and the classical formulation fails. So be careful with this 78 degree formula. If your wavelength of your fluid is in the range of the size of your plate, you also have to be careful with your mass law. Okay, then we use, the next thing is that we use this finite formulation of the plate, and not only the mass formulation, and we use 3 constants of damping in the plate, also 0.1%, 2%, or 10%. And if we do so, we have this typical phenomena. So just imagine that we have a plate of 4 millimeter. For 4 millimeters, the coincidence happens here around 20,000 angular omega per hertz. And you see that if you increase the damping, and this dip is the coincidence dip. So this is where the plate becomes a good radiator. And a good way to do something against that is to introduce damping. So the higher the damping, the less the coincidence dip is. If the plate is getting thicker, the transmission loss, the coincidence gets to lower frequency, becoming more dangerous. And again, the damping fits to it. So just for information, the small lines, that's again just using only a mass matrix. You see why you should always use a limb solution to get the best performance of an isolating plate. So good. Higher thickness leads to higher mass and stiffness. So that means why the coincidence frequency goes low. Damping reduces the resistance dip. And however, all this is calculated for a finite radiation area, but an infinite plate. So this is why this is not a totally correct solution and will not correspond correctly to an experiment. Okay, so that's it. A lot of coupling loss factors, a lot of juggling with wave numbers, discrete and shape functions. It hopefully gave you quite an overview how things are calculated. You have learned many options to calculate this coupling loss factor and all the transmission coefficient. It gives you an insight about how to decouple or couple noise and control features and how to work with noise and control features. The degree of freedom should be carefully chosen for the simple solution, even if it's some such just the radiation efficiency. Complicated panel transmission loss calculations can be easily performed without any field excitation. I mean, this is really the thing. I mean, there are some commercial software that create a very complicated diffuse sound field. You don't need that. Once you know the radiation stiffness, using the diffuse field reciprocity, you automatically have the formula for the transmission at hand. Very important knowledge. Good. So that's it from my side for this very long but important session. Now you're done with all the baselines that you need to perform SEA or hybrid calculations. And in the next sessions, I will give you some examples of SEA simulations, some examples of hybrid simulations, and the whole lecture will end with some industrial examples where I will use commercial packages because a very complicated model only works with commercial packages. Thank you for listening. That was a heavy session. We just have to master maybe finally 3 final sessions. We are nearly through it. I hope to see you again. Have fun and see you then on session 23. Goodbye.